Um, the title of my presentation today is Oversimplification, Creating Meaningless Mathematics. I'm focusing on mathematics because this is an area I know well, but I'm quite certain that the same kind of problems that I'm going to indicate arise in all fields, in all levels, primary school, secondary school, tertiary school. I'm willing to bet quite a lot of money that the same is true in all fields. I'm just not aware of this. So let me first start by quoting Einstein, or at least it's attributed to Einstein. He said that everything should be made as simple as possible, but not one bit simpler. Now, you may wonder why he said something like that. Then, well, I think all would agree that making things simpler is a good idea. It makes things easier to understand, and therefore is a good thing to do. But then, why not one bit simpler? So what's wrong with making things too simple? Well, what does it mean that when you make something too simple? What does it mean to make it too simple? It doesn't mean that it's so simple that it's too easy for the students to understand and they wouldn't have to struggle. That's not a problem in my eyes. But something becomes too simple, oversimplified, when you are actually hiding some information. You make it appear as if it's simple when it's actually not. So let me just look at this explanation or definition that I give here of what oversimplification is. So an oversimplification of a concept occurs when a concept is presented in a way designed to make the concept simpler to understand, but in order to achieve this simplicity, the explanation includes either inaccuracies, or it neglects essential information, or it neglects some underlying reasoning. This is what I refer to as oversimplification. Now, oversimplification can be quite a good thing to do as long as you're honest about it. So let me first give an example of an oversimplification that Einstein himself gave, and this is not contradictory to his other quote that everything should be made as simple as possible, but not one bit simpler. Because if it's obviously clear that you are oversimplifying, then it's okay. So the example I want to give you is the following one. Sometimes 1940s, 50s, I don't know, or the 40s, 30s maybe, he was asked during a radio show to explain how radio works. So this was at the time when radio replaced telegraphy and was quite a new concept, and people were excited about this. And he was a very famous person, of course, and he was asked to explain how a radio works. So he said, well, let's first look at how a telegraph works. And he said, a telegraph is much like a cat. You pull on its tail in New York, and it meows in Texas. A radio is much like a telegraph, only there's no cat. That was his response. This is a gross oversimplification of how a radio works, but it's obvious that it's a gross oversimplification. Nonetheless, it contains important information. It does give you some useful information. First of all, you know that a radio is a complicated thing. Otherwise, Einstein wouldn't give such a silly response. But it does give you some information of how it works. It works kind of like a telegraph, only there's no cat. But the cat, okay, you know that the radio doesn't need cable to transmit and things like that. So it does give you some idea. And this is a good way of explaining a complicated concept by using an oversimplification, because it's obvious, you're being honest. The problem starts when you don't do it, you never do it on purpose, you're not being honest. You oversimplify and you give the perception that you're not oversimplifying. And that's what I want to discuss today, and I've chosen three particular examples of oversimplification, one from primary school, all in mathematics, one from primary school, one from secondary school, one from tertiary education, and I will only touch on the first two. And I would like to start immediately with the first example. So this is oversimplification in primary education. So in primary education, it is customary to teach children how to multiply numbers, usually integers, and at some point negative numbers are introduced, And the kids are taught how to multiply two negative numbers. They are taught, usually in an indoctrination kind of teaching, that minus 3 times minus 5 is equal to 15, contrary to being equal to minus 15, which is, for most people at that age, the first instinct is to say it should be minus 15, because why should the minuses disappear? Our brain sees the minuses and says, well, they cannot just go away. But then the teacher tells them, no, they disappear. Minus times minus is plus. And this is given as a rule, usually with little or no explanation at all as to where this rule is coming from. And there are long lists of exercises, and the general form minus a times minus b is equal to a times b is given. And this is drilled repeatedly, and the kids eventually are able to compute correctly that the product of two negative numbers is a positive number. Now, this is an oversimplification. The reason that this is an oversimplification is because in the teaching of the concept of multiplication of multiplying numbers, there is a rule that is given with absolutely no reasoning. You neglect to give the reason for this rule of multiplication. Now, this is usually done at such a tender age that we produce in this way quite a lot of adults who are able to compute correctly, but they don't know why. So if I ask you now, why is minus 2 times minus 3 equal to 6? Then your first instinct is to quote your teacher from primary school who told you so. He said so, she said so. It's not a very good reason to blame somebody else, right? There is no understanding. Now, what's the problem with this lack of understanding? Now, this is a rather innocent problem, but still it leads to two kinds of complications. So one is that it creates a certain mental picture of the mathematician as the creator of arbitrary rules. I'm the mathematician, so I'm allowed to decide that minus 2 times minus 2 is going to be 6. You're not a mathematician, so you're supposed to listen to me, and I will tell you what's the correct way of doing it. Now, this is not a true picture of what a mathematician does, because a mathematician is not the creator of rules, but the mathematician is rather the discoverer of rules. And the arbitrariness of this law suggests arbitrariness in mathematics, arbitrariness in the subject. And it does not exist. There is nothing arbitrary in mathematics. There is nothing arbitrary in this choice for the answer here. It's just that the reason is never given, it's never revealed. Another problem is that not being able to really truly understand what it is you are computing is a problem. The fact that you can compute correctly doesn't mean that you understand what you are computing. And you see quite often people who need to manipulate numbers, including negative numbers, on a daily basis. The first example that comes to mind is maybe accountancy. And there, because of this lack of basic understanding, there is a horde of rules and rules and rules and rules that are meant to help you manipulate correctly, where none of these rules is actually needed if you truly understand what it is you're computing. So this is just this single example from primary school. Now, the next problem I want to introduce is, in my eyes, far more serious, and this is oversimplification in secondary school, exemplified by the following example. It is customary to have students in secondary education be taught about real numbers, and they are told that the real number has a decimal expansion form, and they are asked to, they're usually shown many different representations of such real numbers. So for instance, the number half can be written as 0.5. The number 1 divided by 10 is 0.1, 1 divided by 8 is 0.125, and there's a really cool phenomenon, 1 divided by 3 is 0.33333, endlessly many 3s. That's a very nice thing. Now, then they are told that manipulating real numbers given in this form is very easy. For instance, multiplying by 10 simply means move the decimal point one place to the right. So if you want to compute 10 times 0.125, then you simply move the decimal point one place to the right, and the correct answer is going to be 1.25, which is correct. They're also taught that comparing the magnitude of two real numbers given in decimal form is very easy, because you just compare digit for digit, and you compare 9 here, 9 here, you keep going, 8, 8, keep going, 8, 8, keep going, 7, 7, keep going, 7, 8, whoops, that's it, 7 is less than 8, therefore this number is smaller than this number, which is correct. These are again given just as rules that are true. Somebody decided, maybe a group of mathematicians gathered in a big room and they voted about which way is the right way. Of course, mathematicians don't do that, but that's again a mental picture that might be related to these things. But now let's have a look at a rather subtle point. What happens when you look at the number 0.9999999, and these dots here indicate infinitely many nines, and you wonder if it is equal to the number 1? This is a problem that I have asked many students in the past years, and almost always I would ask them to vote who thinks that this number is less than 1 and who thinks that they are equal. And roughly 75% of students, and I'm talking about students in 3 different countries now, because I just did this in Fiji a few weeks ago, so that added a 3rd country to my list, but in 3 different countries over the past at least 7 years, 75% of the students forcefully believe that the answer is a resounding no. They're not equal, but rather this number is less than this number. Now that's not surprising because of this way of comparing the magnitude of the numbers. Look, it's obvious that this number is smaller than 1, isn't it? Well, no. 25% of the students happen to believe that they are equal, the two numbers. None of these 25% can indicate why. They can tell me they know it for a fact, but they cannot explain to me why they think that they are equal. Now, let me prove to you that they are equal. Okay, this is the entire argument, so we can go through all of it. Let's call the number x 0.9999999, infinitely many nines. Now we're going to compute 10 times x using the rule given here. So 10 times x is simply the result of moving the decimal point one place to the right, so we obtain 9.999999, infinitely many nines, just using the same rule. Now let's take this equation, 10x is 9.999, and look at this equation. This is our number x, the one we started with. Now let's subtract. What happens when you subtract 0.99999 from 9.99999? Well, all the 9s are going to kill the 9s here, and you're left with the number 9. So the right-hand side is equal to 9. The left-hand side is, you take 10 times x and remove 1 time x, you're left with 9 times x. So if you now divide, you get that x is equal to 1. So we just used this rule, which you believed, and some basic arithmetic to conclude that x is equal to 1. Not approximately, not roughly, not anything except truly equal to 1. Now, every time that I show this to students, some would giggle, like some just giggled now, which is it's a good thing, because it shows that you've learned something surprising. That's good. But quite a few students do not believe this. They find it hard to believe. Actually, if you can surf the internet, if you would do the right Google search, you will find a lot of discussion going on the internet of people who are convinced that they have proven that what I just proved to you is wrong. Because they cannot come to terms with this apparent contradiction. And the reason they cannot come to terms with this apparent contradiction is because it is so deeply grained in their understanding of the real numbers. It looks as if this is a contradiction, but it is not. It is a fact. We just proved it. The reason it's actually not very surprising is that any number, like any object in the world, has different names. So if I was to say now, Ittay Weiss, that's me, that's a way to describe this object, me, right now. But I can also say the only person standing in this room with his back towards the front wall. That's another way to describe me. So here we simply see two different ways to describe the number 1, that's all. So this is already more substantial problem, a much more substantial problem. Also because I have heard first-hand stories of students at the university whose professor set a passing mark for a course at 6.000000, and they have taken the test, and the professor's pocket calculator showed that the grade was 5.9999999, and the professor insisted on failing them. And it didn't help on the student called on all of her mathematician friends to help them convince the teacher that 5.99999 is actually a 6 and therefore a passing grade. The only way to convince the professor was to get her a better pocket calculator. So, just to mention the very last example that I want to include comes from tertiary education, which is maybe very relevant for us here, but every other university in the world. This relates to the problem of integrals and calculus, but I won't get into the details of that. I just want to conclude that usually the reason for oversimplification is a desire to assist the students. It becomes a problem when you're not honest about it. We ask our students not to cheat. We shouldn't be lying to them. If we're simplifying things to a degree which is beyond truth, we should be honest about it, just like Einstein was honest with his cat. So my conclusion is that for the future, the world of education should listen to Einstein and eliminate all and any oversimplification wherever it may lurk, because the dangers it harbors far greatly exceed the advantages it might have. Thank you very much.